So what is a bioeffect? A bioeffect is an undesired biological change to tissues as a result of interaction with their ultrasound beam, and there are two types, mechanical and thermal. So some of the basic differences with the bioeffects. With thermal, they are related to a temperature rise over time, and the risk is greater with non-scanned modalities, such as continuous wave, pulse wave, and A mode, because they have a longer listening time. With thermal, an increased scan time gives you a higher risk of bioeffects. For mechanical, it's related to cavitation and the threshold effect. The risk is greater with scanned modalities such as 2D, M mode, and color, where you would be scanning for a longer period of time with a higher intensity. And for mechanical, a higher intensity gives you a higher risk.
So this diagram shows potential bioeffects from ultrasound that delineate safe and potentially harmful regions according to ultrasound intensity levels and exposure time. The dashed line shows the upper limit of intensities that are typically encountered in diagnostic imaging. So it just basically shows how increasing intensity levels and increasing exposure time will produce bioeffects.
Measurements of power and intensity. There are many different methods to measure the intensity of a sound beam. Some of these measurements include peak intensity in space, average intensity in space, intensity taken over the shorter duration of the pulse, or pulse duration, intensity taken over longer duration of the pulse, plus listening time, or pulse repetition period.
So it's important to understand what some of the important intensities and their meanings are. So the nomenclature of intensities is described using a four-letter phrase attached to the end of an I, which of course the I stands for intensity. So the first two letters of that four-letter nomenclature are always how the beam is spatially distributed. And the second two letters of that nomenclature is always how the temporal resolution is distributed. So some of the most important intensities that we should know include the ISATA, which is the lowest intensity because it's spatially and temporally averaged, and averages are always less than peaks. So in turn, the greatest intensity would be the ISPTP because both spatially and temporally they're both peaks. And then, as mentioned earlier in this PowerPoint, the greatest risk for thermobioeffects is the SPTA, and the greatest risk for mechanical bioeffects is the SPPA. And then the maximum intensity is just the IM.
So which intensity has the greatest likelihood for thermal bioeffects? That's going to be spatial peak temporal average. So the highest intensity over space is averaged over the whole length of the pulse, giving it a greater chance of thermal bioeffects.
So the intensity that has the greatest likelihood for mechanical bioeffects is the ISPPA, which stands for the intensity of the spatial peak pulse average. So the spatial peak is the intensity at the highest peak, while the pulse average is the average of all of the intensities that occurred over the pulse duration. So since it takes time for mechanical bioeffects to happen, because cavitation takes time for the bubbles to form and then eventually implode, that's why it's spatial peak and the pulse average, because it has to be over time and it's not instantaneous.
Thermobioeffects were discovered in 1917 when a fish died after it was exposed to ultrasound. Then in the 1940s, thermobioeffects were used in surgery to destroy cancerous tissues. The American Institute of Ultrasound and Medicine and the National Electric Manufacturers Association and the Safety Standard for Diagnostic Ultrasound Equipment acknowledged the biological effects of ultrasound in 1983. And finally, safety standards were established in 1993 by the AIUM, namely the standard for real-time display of thermal and mechanical indices on diagnostic ultrasound equipment, commonly referred to as the output display standard.
History of mechanical bioeffects. Ultrasound is one of the fastest growing imaging modalities due to its non-invasive nature, low cost, real-time imaging display, and many other things. The FDA has been the regulatory body in terms of the acoustic output of diagnostic ultrasound. They regulate the maximum output to a level through a process that makes current devices the equivalent in output to those produced prior to 1976. This allows a safety margin for diagnostic ultrasound while still making it medically useful. This process has made it possible for there to be 0 instances of mechanical bioeffects in patients from an ultrasound exam since it has been used as a medical tool. The AIUM has since had conferences to assess the scientific evidence of mechanical effects that could happen in the body, including cavitation, and has released scientific information and recommendations concerning safety while using diagnostic ultrasound.
So some safety guidelines for bioeffects. For thermal, no intensities should exceed 720 megawatts per centimeter squared. The temperature should not exceed the thermal index set for specific imaging presets. And a higher duty factor has a greater risk of causing bioeffects. The duty factor is pulse duration divided by the pulse repetition period, which is the percentage of time sound waves are transmitting from the source. So the longer you have the sound waves transmitting, the higher risk you have for having thermal bioeffects. With mechanical bioeffects, no intensity should exceed 190 watts per centimeter squared, and tissue heating should not exceed 40 degrees Celsius because cavitation occurs at 45 degrees Celsius. And a higher beam uniformity factor has a greater risk of causing mechanical bioeffects. The beam uniformity factor is the spatial peak divided by the spatial average, which is a measure of how uniform a beam is distributed spatially. A more uniform beam will be more focused and will have a higher chance of causing mechanical bioeffects.
So there are 3 different thermal indices that best estimate the risks of developing thermal bioeffects. TIS, which stands for Thermal Index in Soft Tissue, predicts the temperature rise presuming the predominant presence of relatively homogeneous soft tissue. TIB, or Thermal Index in Bone, will predict the value for bone presuming that the surface of bone is near the focus of the beam, as it occurs commonly in fetal imaging. And then the third is Thermal Index in Cranial Bone, which will indicate the likely worst-case temperature rise for a bone at the surface, such as the cranial bone when performing transcranial imaging. These predictive values that estimate the max temperature rise anticipated for the current imaging situation. And there are 3 different thermal indices due to the fact that absorption rates vary greatly depending on the medium. So for example, a thermal index of 1 will imply that the maximum temperature rise expected is 1 degree Celsius.
So when we talk about mechanical bioeffects, we're usually referring to 2D imaging because 2D imaging has the highest risk of producing mechanical bioeffects. So the way that we get an approximate measurement of how much mechanical bioeffects is going to happen is something called the mechanical index, which the equation for the mechanical index is the peak rare fractional pressure over the square root of the operating frequency. So if you look at the relationships in the equation, increasing the operating frequency would decrease the mechanical index. So going based off of that, the risk of cavitation increases with lower frequency transducers and vice versa.
Intensity measurements in relation to pulse and time. Recall, duty factor is a percentage and represents the amount of time that the pulse is ringing. Duty factor can be calculated through the pulse duration divided by pulse repetition period, and for bioeffects, the temporal average divided by the pulse average.
So the AIUM has developed safety standards and regulations for safely performing ultrasounds. The principle that they've come up with is ALERA, as low as reasonably achievable. This is the principle of only doing what is clinically necessary to obtain images by using the lowest setting possible, not performing unnecessary scans, and keeping scan time to a minimum.
Thankfully, there have been no recorded biological effects observed due to the normal temperature rises less than or equal to 2 degrees Celsius above exposure duration up to 50 hours. The AIUM's statement on ultrasound safety indicates that the prudent use of the ALARA principle will make the benefits of ultrasound outweigh the potential risks, should there be any that are found.